We have moved on to part 3, linear system identification. This is 260, lecture 14, parametric linear system identifications. So last time we discussed the non-parametric system identification, and that's basically identifying in time domain an impulse response, and the frequency domain, basically frequency transfer functions. And then we used a little bit of sophisticated technique based on a correlation method. And Wiener-Hoffe equation is the foundation behind it. Now we look at the parametric linear model, and the first question is, well, why parametric? And we have already covered the things in non-parametric area. So let's think about the non-parametric ID, like a body plot and an impulse response in particular. So linear time invariant systems, and then this is the impulse response, convolution form, right? And then factoring out the time shift operator, so we can get the transfer operator or transfer function, basically. Now, let's think about the particular situations where these actually impulse parameters are, and the first one starting with the G0 and the G1, G2 are taking this actually values. First one is 1, and then 1/2, and then 1/4, blah, 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 okay? So let us take this example. We need the infinite number of parameters to represent this, right? Now, interesting things are following. So let's multiply 1/2 Q inverse to both sides. So 1 times this one is actually 1/2 Q minus 1, and then this one becomes this, right? And the third one as well. So at the end, let's add the 1 and then subtract the 1. So I did nothing here. But I know if you look at it from here all the way back here, this one is nothing but the same one as this. That's actually GQ. So this as a whole equals GQ minus 1. So looking at the first equation and the third, the final expressions, we can solve this equation for GQ. You get this answer, right? 1/1 minus half times Q inverse, right? So if we know this structure, that this structure can be written in more general form, GQ equal 1/1 plus CQ inverse, right? So if we know this structure, all you need to do in the system identification is just to estimate the one parameter C. Instead of infinite number of parameters, if you take this expression, which is actually coming from impulse response, right? So this is very much, extraordinary case, but in general, a system can be represented with a more succinct model containing fewer parameters. If we know some model structure, knowing some model structure, we can actually bring in some parametric structure, then we can represent it in a more condensed form. And as opposed to non-parametric ones, actually the number of parameters involved is infinite, so we call that the non-parametric. There's no structure. It's very general, but there's no structure in it. But if we have some prior information as to the system looks like something like this, then we can actually focus on the estimation of only these parameters. In a more general case, we have, say, denominator side A1 to ANA, and then numerator side B1 to BNB. These are the parameters we would like to estimate. But it's fewer than the infinite number of parameters. Okay, good. So that's one thing what we like to do, parametric system identification. Then the other interesting point is that in control design and estimation predictions, we did some estimations and mostly based on the common filtering. It is often important to identify not only the dynamics from input to output, but also noise dynamics, how noise and the disturbance perturb the systems, where noise really comes from, and whether the noise is colored or correlated or uncorrelated. So these are things that we need to know. So we just broaden the scope of the identification work to characterize or identify the noise dynamics, noise properties. So various techniques have been developed for identifying both forward pass input to output dynamics and the noise dynamics, as shown here. Okay, now what is the noise dynamics? Now, how we can really characterize the noise dynamics? This is a very unique point when we do the parametric estimation and identification. The fundamental difference between the input-output, the forward pass dynamics versus the noise dynamics is that the input is accessible for the forward pass main plant dynamics, right? And we can actually manipulate the input in that. But the noise dynamics, noise is noise. It comes in. We did not invite them to come, but noise comes in. And then the noise is basically, basically a random process, right? So, shall we give up? No, that's something that we can do. So, although the noise is not directly accessible, but the noise had some statistical properties and some structure. And this last part, the structure, is something that we like to identify. So to capture these properties, in particular structure, we consider the following noise dynamic model. Okay, so this is the big hypothesis, but we basically assume that the noise that comes in, which is somewhat observable or something, we can actually, it's tangible here. It's basically originated in some random process that's actually white noise, okay? Uncorrelated, totally uncorrelated white noise having this power spectrum, okay? The lambda, strength lambda. Okay, and then going through some dynamic process. Here we assume the linear model, so transfer function type of dynamics HQ is involved that result in the VT. So we assume that the noise is originated in a completely uncorrelated white stochastic process, ET, with the covariance lambda, and that is actually that goes through a transfer function HQ, resulting in the colored noise VT, which we get. Okay, so the reason why we actually bring in this structure is that the white noise is basically, completely unpredictable. We can't do anything, okay? But in somehow, after going through some dynamic process, HQ, VT tends to be colored. If you take the, power spectrum, it has, some, some, specific shape here, right? And then autocorrelation too is not just a single point, but it has some, elements, in there, just as we look at the last time. So, VT may be colored, and then colored noise is to some extent predictable. If we can actually identify HQ, we can actually predict this in a VT to some extent. So what we like to do is to identify this noise transfer function HQ representing the structure or the channel through which the noise comes to the system, and and we differentiate it. We differentiate something totally unpredictable versus something from structure we can predict. We can actually access this problem in this way. So the various model structure that can be considered for stochastic linear time invariant systems. depending on how input and output are connected, and then how noise comes into the system, various structure can be considered, right? And here we have A, B, C, and these are all basically, polynomials with the finite number of parameters. Say AQ is 1 plus A1Q minus 1. So 2 times and 1 time shift operator here, and like this, and all this, like this. Okay, the first one is called the autoregressive model with the exogenous input, and we take ARX model is shown here. So for the pass the dynamics, first going through Q, BQ, and then actually 1 over AQ, and then output. Noise channel comes in here, and then the ET is going to here. And the ET is basically the white noise. Okay, white noise, uncorrelated one. Now, our max model, it's called the autoregressive moving average model with exogenous input, having this structure, is very much commonly used. This one is maybe most popular model, where the original white noise go through some dynamic process, CQ, then maybe fed into the process, and then actually it is to perturb output to YT through this channel. Okay. Now, there are many other models like Box-Jenkins. The model is basically 2 channels are completely different through different transfer functions. And FIR model, the difference is that AQ is actually 1. AQ is not actually showing anything, just a BQ. So this one is finite impulse response, the type of model with some colored the noise dynamics that comes in. This particular part is also very useful as we discuss it the next time. So we focus on the ARX, RMAX, and then FIR, FIR model, today. Box-Jenkins model, having a little bit of the different type of treatment is needed, and we will not cover that in class. Okay, so now estimating model parameters from input to output data. So what we like to do is to estimate, say, if you look at the forward pass, A's and B's are involved, so we like to estimate these, right? And then we like to use the prediction error method. We've been using this repeatedly. We use the same framework here. So real systems, output to YT, and the model predicted one is Y hat, T, and theta, which is actually depends on the parameter values it is to use. And we look at the prediction error, and then based on this prediction error, we like to estimate the parameter value theta. So we use identification data, UT and YT, the T go 1 to capital N. And then what we'd like to do is basically, there are many methods, but this one is to use least square estimate. So this prediction error squared is to be minimized by properly selecting a theta. That's actually optimum, parameter values. That is actually the model we'd like to identify over here. You see the almost exactly the same expressions when we move to neural nets and then the learning process. Well, the neural nets, the emphasis is basically nonlinearity, and actually a system identification of this type is basically dynamics. Then that's actually the difference. But formulation is very similar. Okay, now let's look at the autoregressive model with exogenous input, the ARX. So, ARX model, as I showed before, ET comes into this directory and then going through the process, okay? So, AQ and BQ are polynomials, okay? Like this. With BQ, we start with the B1Q and minus 1. And then A is starting from 1, okay? so through this, output YT can be written, through U BQ times, this one. So that's BQ over AQ UT. And this ET goes to the 1 over AQ, and then added to this. So that's first multiply AQ to both sides, and then you get the AQY equal BQU plus E, okay? So this can be written in this way, because if you think that the AQ is given by this, time shift operator here. So maybe from here to here, it's a little bit, you need to get familiarized. So let me just show some actually example how you go about this. So let's see AQYT, we'd like to compute this. Now, A is now simple case 1 plus A1Q, minus 1, only one term over here, okay? So remember that this one is a time shift operator, and then this kind of operation is basically linear. So YT can be distributed to each of them. So first you get the YT, and then second one, YTs with this operator, right? So this part is basically what this says is what? Just the shift the time minus 1. So YT replaced by T minus 1, YT minus 1. Okay, good. So now if you look at the previous case, ARX model, YT equal B over A UT plus 1 over AET. So we cleared A, getting this one, right? So how do you compute this? AQ? Inside of it, we have this kind of stuff. So first 2 terms are something like this, right? Now here in this expression, I moved this term to right-hand side. So YT minus A1, YT minus 1, and then the flow AQ has many terms. So we have many terms, minus ANA, YT minus NA, the last term. Okay, B1, U2, B1 is actually starting with the B1 Q minus 1 that result in B1 UT minus 1. And the last one, the BNB, UT minus NB, NB times time shift. And then added the Y, ET. So that is the equations, I wrote here. Okay? So, the next one is we would like to have a, predicted value of YT. And then we like to compare that one against an actual measurement. You see this kind of formulations. We like to create the predictions and compare that one against the real measured one, and then evaluate this guy, right? So yeah, we would like to based on this, we like to establish the prediction. So here's the with the hat, that means actually the prediction. And here, I just put the hat to each parameters, A1 to Bn, with hat, because these are not the true ones, but an estimated ones, just to differentiate these. This is the true system, but this one is predicted one. And also, you notice that the ET disappears here because the ET is actually, totally unpredictable. So I just eliminated that, okay? Now, if you look at this, interestingly, parameters you want to estimate, the B1, BNB, and then A1 to ANA are linearly involved in this expression. So this is good news? Yes, this one is extremely good news because we can write this output prediction and actually as a linear regressor, the linear regression like this. Linear regression. So I use the theta and then the phi, regressor and then parameter vector notations. So first I put all the parameters into this vector theta. And actually pairing with this, regressor terms are actually identified in this way. So the first one, A1 times minus YT minus 1, right? And then here, ANA, YT minus NA. And the B terms the same if you want to be this, this way. Okay, so theta is basically factored out, and it's linear. So what you need to do is actually you can evaluate this, and you want to actually minimize this given a you know identification data, YT, UT, real measurement, YT, and then actually input you use, input output data, and then you can actually use this to to construct this guy, and then you need to find the theta that is to minimize this. And since theta is linearly involved, you can immediately get the the optimal value, which is given by this. This is just a standard least square estimate, right? Now, just one note is that the T star here is basically it does not actually spin from T equal 1. Do you know why? Because if you set the T equal 1, this is Y0 and 1 Y minus NA, which is not available, right? So you have to shift this one, start computing this after NA and NB, whichever the largest. So this is kind of an edge effect. You experience this in the previous assignments, right? So we had to do that, but that's my minor point. The point is that the ARX, is basically best predictor is linear regression, and we can actually apply the least square estimate to get the the optimum single unique optimum parameter values. Cool. Now, little the discussion here. Yeah, in this ARX model, the output prediction was obtained simply by taking the expectation of the true systems, right? So here's the true systems, and we basically took the expectation, and that's a reasonable thing to do. And these are basically and the ET is separated out, and we can assume that the the mean value of ET is 0, so that's why we skipped this guy, omitted this, and then end up with this, and then that's a result in the linear regression. That's good. But now this is a very special case where the white noise ET alone is added to the output. In general, this is not the case. And for example, if you have ET plus one-time shift ET minus 1 is added to this. So this is somewhat the more colored noise that comes into the system. Okay, you can't actually take the best estimates to be just eliminating these two and then set up this. In fact, this is not the best estimate that you can make, and I'll show you why. And then actually, if you use this, you get the biased estimate of the parameter values. So as shown in the following, the term ET minus 1 is somewhat predictable after you observe YT minus 1 and then knowing the input you provided, UT minus 1. In the prediction error method, we must make the best estimate to evaluate the parameters. Now, let's actually, let me elaborate on that, the last statement, okay? It said that in the prediction error method, we must make the best estimate to evaluate the parameters. Why is that? Well, so, here's the actually your actual measurement, right? So if you ignore this guy, which is actually colored, and just naively predict this guy based on the model you pick, then that's not actually correct the best you can do. And if you use that one for this parameter estimation, you get the biased one. So that's it's saying if the prediction is not an optimum for a given parameter theta, the prediction error is due to, well, basically if you just simply evaluate this, that error comes from partly from the inappropriate prediction that you are making. Basically, there's some this parameter theta is not properly involved here, or actually the structure is something wrong, or actually the parameter you use, the parameter values you use, the theta is wrong. What we like to do is to say that this guy, creating some error because the parameter values you use are wrong. Therefore, parameter values are to be corrected based on this, right? So, first, we have to make the best prediction we can make. So how can we really go about that? That is a question. Okay. In fact, if you don't use the correct predictor, you end up with the so-called biased estimate, which is bad. Okay, so in doing so, this is the point we actually introduce the kind of interesting concept. Sometimes students cannot actually accept or observe this concept, but it's a very important part. So let me do my best to explain this. So yeah, first we assume that this kind of a dynamic process HQ, right? EQ and HQ, right? So that is added to this. So first of all, yeah, we assume this ET to be white noise with the variance lambda. So the lambda is actually strength of the original white random process, right? And then we model the colored one, which is actually coming to the output directly. BT is given by this. So now here just one point. We assume that the first term of HQ, let's say HQ is actually defined in this way. The first quotient term is this guy, and without loss of generality, we assume the first term quotient is to be 1. The reason is that since the magnitude of this guy is represented in the ET's variance lambda, right? So we don't have to actually model this twice in terms of the magnitude here and here. So magnitude is all involved in ET, that's actually lambda, okay? So that's why we assume that the HQ to be having a first term 1. And such a polynomial having the first term 1 is called monic. Yeah, in fact, it is actually this guy is the highest order because out of the q minus 1 q to something. So highest order quotient is 1. That's called the monic. Okay, so now predictor. Now here the thing is so if we model this noise dynamics HQ, we can predict this colored noise to some extent. And let me explain why and then how we can really do that, right? So in an attempt to find the optimum output predictions, we have to consider the actually best we can do. So utilize the observation of a prior output YT minus 1 and then UT minus 1. So if you write out the output YT coming from these two pathways, we can write the YT GQUT plus HQET, right? And then one time step back, we can write out the similar equation, YT minus 1 equals GQUT minus 1 plus HQET minus 1. So we say that the E is actually totally unpredictable. However, if we look at the ET minus 1, this guy, since we can observe YT minus 1 at the time T when we like to predict the output. But I know we have already observed the YT minus 1, and we know what input we provided. So these are known. So we can solve this one for ET minus 1 to estimate the ET minus 1. Here we are, putting this one at one side and divided by HQ, we can estimate the ET minus 1. Other ET minus K in general can be predicted in this way. If you have the measurement and the Y and then input the UT in this way, right? So what we'd like to do is suppose HQ is given by this type of impulse response form, right? Impulse, and then it is basically assumed to be monic and 1 or sitting here. So the colored noise VT can be represented, ET multiplied to each terms, C, time shift element, time shift operator is used here to create the ET minus 1, the ET minus 2, so far. We can get this expressions, right? Yeah. So now these terms, the first one, ET, is we can't do anything. This is totally unpredictable. But I know all the other terms, ET minus 1, ET minus 2, all predictable because we have already, observed YT minus K, and then we know what the input we used. So in a sense, we can predict all of these except for this guy. Yeah. So let me just, replace this one, by MT minus 1. We just wrote all these terms sitting here. This should be predictable. So in doing so, I just did the somewhat one technique plus ET minus ET. It just did nothing. But if you look at from here to here, this is nothing but the H times E, right? H times E, and then minus ET. So factoring out the ET, HQ minus 1 times ET. Okay, since the HQ is monic, first term is 1, 1 minus 1 is 0. So it starts with the, H something on Q minus 1. So it starts with the, ET minus 1 and the ET minus 2, so forth, not actually including the ET. That's obvious from this expression. So estimation of the colored noise, BT. BT, is basically something totally unpredictable plus predictable. So we can actually divide this one into this, and then this one we give up, and then it means 0. So this is predictable part. And this guy, as just we obtained over here, the result HQ minus 1 times ET. That is the ones, we can use over here, right? So now let's see ET. So I just wrote this one again. So YT equals GU plus HE. So H times ET equal YT minus GU, right? So ET is actually divided by HQ both sides. This is the term to replace ET, right? ET, right? So now distributing this one to this, 1 minus H inverse times Y minus GUT. So if you observe in Y and then U, we should be able to predict this part to this extent. Now, what, then we puzzles, we observe YT minus 1, and then we know UT minus 1. YT minus 2 is okay, but YT is involved. So what's the point? If we need to know YT, this is not valuable to do, right? However, this is 1 minus H inverse, so this may be 1 minus 1. If this H inverse is monic, then there's no terms, constant terms. So Y start with YT minus 1 mostly. So let's check out whether this guy is monic or not. And that's very critical, whether we have to know YT to predict the VT, no, or, YT minus 1 is, T minus 2, T minus 3, so only the things we need. So let's write this inverse H is to be something like this, impulse response expression. And this is the inverse, so by definition, if you multiply this, it should be 1, right? And then actually expanding this, this times, HQ, we get this kind of expression that we just look at the constant term alone. 1 comes from HQ, which is monic, and then H2 there 0 is the first term, so it comes from this inverse. That product of these two alone is involved for the constant terms. Okay, and then this must be 1. So this must be 1. Otherwise, this cannot be held. So we can conclude the H through there is 1. That said that the H inverse to mnemonic. H is a mnemonic, then H inverse to mnemonic. So that's good because this, 1 minus HQ inverse, 1 minus 1 cancel out. So it is start with the Q minus 1. So YT minus 1, YT minus 2 are all involved. That's a function of these. That actually we can use for prediction. Good. So, this is the, the BT minus 1 is given by this, that what we just obtained. Okay, this obtained. So by adding this for the path, we should be able to predict the output, right? So GQUT plus this term is expanded in this way, just as we obtained. So let's compute this. So first, this times this guy is sitting here, but now I distributed this one to 1 and to this. And the first one, the GQ minus GQUT, and plus minus plus HQ inverse GQUT, right? So these two cancel out. So the best predictor is y hat t minus 1 equal HQ inverse GQUT and 1 minus HQ inverse YT. Maybe you have no clue why this one is to be able to predict the output YT in, to its full extent. Well, first of all, let's check out whether this guy is the best we can do or not. Okay, so to do that, let's basically compare YT minus Y hat TT minus 1. If we know G and H correctly, this should provide the best estimate and how it looks like. Let's check out, okay? YT minus this one, I just wrote this one in here, okay? Two terms comes in here and here. Okay, now first break out this guy YT minus YT sitting here, okay? And the rest part, the plus and H inverse YT is sitting here. Okay, and then this one is just, sitting here. So this YT cancel out. And the rest part, we can factor out the H inverse. So if you factor out the H inverse, the remaining part, YT minus GQUT. What is YT minus GQUT? Again, let's look at this. Y equals GU plus HE, right? So Y minus GU is actually HE. So this part is basically H times E. So replacing this one here, canceling out the H and the H inverse, just leaving ET. So what does this mean? We compare we thought that this is the best, predictor, difference from the actual measurement, which comes from the true systems. This prediction error, if we know these parameters properly, correctly, the prediction error is nothing but white noise. What does this really mean? This one indicates that the Y hat to TT minus 1, this is our best predictor, is really the best that it can do. Of course, we cannot go beyond ET, but all the other things that have been actually taken care of in here. So in other words, we have some actually noise dynamic process here. Some structure is involved here, right? So if we take the all information that you can take from the the systems, the rest of the part which is unpredictable is just the ET. That's garbage. So we measure the YT and the UT, everything that you can use. You take all the information which is meaningful, and having some structure behind it. After you do it, the rest of the part is basically the predictions error that you still have is nothing but just the ET. So we can say this is the optimum, the best prediction. It's called the one step ahead, predictor. So with this, we should be able to, we should be able to do this. Now we have the best predictor, make a comparison between these two. Then we can actually, estimate all the parameters involved. Okay. So now, yeah, but this particular part is all kind of a long equation and kind of strange. So, yeah, let me just work out one example. Then I entertain some questions. So this example, yeah, an improved robotic airplane, basically drone that can fly against the gusty wind is being developed. Yeah, the research team attempts to build a stochastic dynamic model to quantify the wind properties, and they use a wind model to better, predict the airplane behavior and better handle that the gusty wind. The overall system is modeled as a stochastic linear time invariant system with a discrete time transfer function GQ, HQ, and input UT and output YT, and the wind disturbance is basically color, the VT. And ET is actually white noise. And we assume HQ is to be monic. Yeah, first in the aeronautics, literature, gusty winds have been modeled in many ways. There are many, parametric models being suggested. Yeah, it's important for safe aviations of airplane. Okay, so let me just start with a very, very simple one. This one is just, in a sense, a toy problem, but it works pretty well. HQ equal 1 plus CQ inverse, okay? And then we assume that the forward pass BQ minus 1, and then this GQ is 1 over 1 plus AQ inverse, okay? The question is obtain the one step ahead the predictor of the output, the YTT minus 1. As a function of input UT, and then actually, output YT that we can observe, okay, the YT minus 1. And also, maybe we'd like to know prediction of a VT so that the airplane or a drone can handle the gusty wind in a better way, all right? So let's look at that. Now, just to slow down a little bit, and then also, yeah, yeah, things are a little bit easier to understand. Let me just use this my handwritten things. So the problem is that we have yeah, B okay, B and yeah, we have some gust comes in with E and from E, and then this one goes to another process, G, resulting in Y, right? So that this is the case in a U, okay? So now, yeah, the problem said, this structure is a little bit different from the one we discussed. So let's actually change this, so for the pass is the B and the G. So let's put together B times G. And here, this one go through G2. So, H times G is the process that you had to go through, right? So this is B, and this is Y. This is input to U. Okay, this is E, right? So, let's see, in the previous notation, this one is actually G, and we'd like to describe the G tilde, and then this guy, H tilde, okay? H tilde. And the G tilde, with the given parameters, actually B times G, B was actually BQ minus 1. So this one looks like BQ minus 1. Ah! No, please. Don't do that. Cancel. Okay. So yeah, and then 1 plus AQ inverse, right? And then this H tilde is basically, for the pass H is 1 plus C q minus 1. And then this guy is 1 plus aq minus 1, right? Okay, cool. So yeah, predictor that we obtained yt t minus 1 is basically h inverse gu plus 1 minus h inverse and y, right? Just to avoid confusions, this is basically this lumped one. So I just put the here. So y this guy is basically yeah, h inverse is this one. So 1 plus aq minus 1 plus cq inverse, and then g is this guy, bq minus 1 plus aq minus 1 times ut plus the 1 minus h, flipping this, 1 plus a yt, right? So these two cancel out. So let's actually multiply 1 plus cq inverse to clear the denominator, y hat t minus 1 equals bq ut plus this one, I think c minus a q inverse yt. So writing out this guy apply this time operator, we can write y hat t minus 1 equals, moving this one to left hand side, minus c times 1 times shift plus b u t minus 1, and c minus a y t minus 1. So this is the prediction that you can make. If you know a, b, c, you can predict the output y very accurately. You can also do the same thing for v hat. The v is to be predicted, prediction value. This may be more interesting, right? You want to predict the ghastly situations. So even though it is actually unpredictable to some extent, but well, as you see, the gas is actually increasing. You expect the next instance too, it is actually to be high side, right? So there's some kind of dynamics involved. White is something totally unpredictable. Every time slice it's changing, right? But the colored one is not. It's not the case. So B had we obtained 1 minus h to the minus inverse times y minus gu. You can do this same thing as you did in here, this process. You can do the same thing for this, and you can find the sum actually predictor, but we had the t minus 1 equal to some functions of your previous and b t minus 1 and 1 t minus 1. You can write these things in here to predict the wind. So that is what we have been doing. Okay. So with that, any questions up to this point? Let me just check your, yeah, so this one is a little actually involved, so there's no questions, and it's hard to raise questions. But anything that you need to clarify a little bit?
Professor, I have a question.
Sure, go ahead.
If the noise, the E of t that is brought into the system, if that's not a zero mean,
yeah, sure. That's a good question. If zero, if not the zero mean, you can just shift the the coordinates of, let's say, the output y.
Okay.
Yeah. So dealing with this random process, almost always we can take out the mean values. The situation is a little tougher when actually mean varies up and down. That's actually not the stationary process. But as far as we assume that the wide sense stationary process, so that we can define the autocorrelation and so forth, the process is assumed to be wide sense stationary with the constant, not necessarily zero, constant mean value, right? So that constant mean value can be incorporated into the y or any variables that you use, so we can eliminate that effect. So without the loss of generality, we just set the mean value to be 0. Yeah.
Okay, thank you.
Sure. Okay, with that, let's move on to the last part. So next one. So when we now know that the the best predictions of for Armax model. So but by the way, as I said, this one counts. ET is not directly brought into this line, but through this dynamics CQ. So this one is autoregressive moving average model. Okay. So the output of the Armax system is just writing out this equation based on this diagram. We can write it this way. The C is defined here, and the prediction is given by this, right? So interestingly, yeah, here's the actual prediction error method. So upper part is actually true systems, okay, true systems. And the lower part is what? This is the model, and then predictor. So now we found the best predictor that is actually predict the things the most the best we can do, to the extent that that is the prediction error here supposed to be just white noise. Okay, if we have the correct parameter values, A and B and C are actually including lots of parameter values, right? Parameter values, which we like to estimate. So if those parameter values are correct, this prediction error is to be what? ET. That's actually all just the garbage information in here. Okay, and all the rest of part is due to the mismatch of the parameter values sitting here. If this model is correct, okay, if this model is correct, okay, then actually the error more than just white noise error is due to the parameter mismatch in here. Okay, so with this, we should be able to find the best values for A and B and C. Now, interesting point is actually this also include the C, which comes from the this noise channels, right? So what is the benefit you can enjoy? We can identify not only the forward path dynamics in A, B, but also the noise dynamics C. C over A is actually noise transfer function comes into this process, right? That can be identified too by doing this actually prediction model. So that's actually interesting part. We can actually simultaneously estimate and determine both forward path dynamic model and the noise dynamic model. Okay, so let's work out that one. Now, however, let me just use a little bit of different notation. I said y hat t slash t minus 1, but in fact, this is actually prediction. It is actually based on the estimated parameter values of theta. So let me write it to emphasize that y hat t theta. Okay, so now we found that the best predictor is given by this y hat t slash theta is given by this. It's the functions of all parameters A, B, C sitting here. And then we use no input that you use and then observe the output YT. Okay. So now, yeah, first, multiply CQ to both sides, clear the denominator. And, yeah, we like to move this one to right-hand side, except for the first term, which is actually y hat t, theta. And the rest of the part must be moved here. So that's why actually, 1 minus CQ is basically, C is basically, monic. So this one starts with the y hat t minus 1. Okay, and the rest of the part is BQUT, and then this one. Okay, yeah. So yeah, last time when we dealt with the ARX model, this predictor is nothing but just the linear regression, where parameters to estimate the theta can be completely factored out, and the remaining part is regressor phi, theta and phi are separated, right? But now bad news is that this yt is a function of theta. Previously, C was just 1, so this term did not exist for ARX model. But, our max model, unfortunately, we have this. So turns out that this cannot be written in a linear regression form. So we wish to write this one in this way, but no, we can't write it, So we had to do something. So now it's an identification of our max model, autoregressive moving average with exogenous input. Well, here the moving average, for the noise channel go through a C, Q. So that's basically moving average part. Okay. So now let me just rewrite that, write it here again. Y hat is C minus 1 minus C y hat, and a BU C minus 1 YT 1 minus A YT. Yeah, I just subtract YT and then add the YTs, a little bit different equation than the previous one. But now we can actually, factor out the C minus Q, and here combining this term and this term, we have C minus 1 times YT minus Y hat, sorry, and screw up, Y hat and here, Y hat and here. And the rest of the part is 1 minus A YT, and then this one just to translate from here to here. Okay, now, as I said, this guy is a function of, actually, it depends on the theta. So, yeah, we cannot write it in just a standard, linear regressor. But it's still good news here is that the C here in a 1 minus AQ is basically, skipping the first term. It should be minus A1, Q minus 1, minus A2, Q minus 2. And the A's are linearly involved in here, right? And here, starting with the B1, Q minus 1, and then B2, Q minus 2 times U2. So that's actually B's are all linearly involved here, right? And then this term too, CQ is monic, so minus 1. Let's start with the C1, Q minus 1, C2, Q minus 2. So, this term too is basically C's are, kind of, linearly involved. So if this guy is, we treat it as a kind of one variables, this one can be represented in sort of a pseudo linear regression. So in doing so, let's actually define epsilon t. This is basically prediction error to be new variable epsilon t. We can write this equation into this form, right? So first one coming from A1 YT minus 1, right? And then this one expanded to B1 UT minus 1, the B and B UT minus N. Here we go to this term, starting with the C1, and then we replace this guy as epsilon t minus 1, right? The first term is actually Q minus 1, so time shift. epsilon t minus 1. Down to, oops, yeah, this is a typo. Always I have some typo. I'm sorry about that. This should be epsilon t minus nc. Epsilon t minus nc, slash theta. Sorry about that. Yeah, I wrote in this one here, the t minus nc. This should be, corrected. Okay, so we put together all the parameters to estimate A's, B's, and C's. Okay, these are the set of parameters. And this regressor part, it's not just the pure, regressor phi t, but phi t slash theta. Picking up the paired terms, we pick up, minus y t minus 1 to minus y t minus na as before, and then ut minus 1 to ut minus nb as before. And here, these terms, epsilon t minus 1 slash theta to epsilon t minus nc slash theta. Okay, so apparently, if you use this regressor, we can write it in here where theta is somehow factored out. So we call this a pseudo linear regression form. Pseudo linear regression form. Okay, so now how we really estimate these parameters? We cannot use the least square estimate in its original form, but in fact we can do some kind of a clever extension. It's called the extended least squares and estimate. Okay, so with the pseudo linear regression, the prediction error method becomes a non-linear optimization problem where the standard least squares estimate cannot be applied, right? Because this is not actually pure linear regression. So we use something, little technique. It's the type of a bootstrap method. Because the problem we're facing is kind of a chicken and egg problem. Yeah, if we know, in this way, we'd have to find the theta, right? But theta is needed to construct this. So that's a little the chicken and egg. So to break that logical circular logic, we basically start with some best estimate for theta, and then using that theta, we construct this phi t theta, and then using this guy to predict the theta value, and with that the new better theta values, we construct this y hat again, and then actually do the second round minimization of this. Okay, so how we can get the first estimate? Now, one technique here, the extended least square estimate, is first assume that all quotient of C's is basically the 0. In other words, CQ is just 1. CQ should be 1 plus C1, Q minus 1, plus C2, Q minus 2. That's actually the CQ. But let's start with the bold assumption that the CQ equal 1. If that's the case, the problem reduces to ARX problem, right? ARX problem, CQ equal 1. So basically, ET, white noise directly comes to the systems. So, that's ARX model, which has the, unique optimum solutions, right? Because that is a convex optimization problem. So that's easy. And we have basically unique solutions to that. So let's use that actually values of A to A's and B's for the initial set of theta values. Okay, And C's are assumed to be 0. So setting this, all the A's, B's, theta bar, solution from the ARX problem, we set the theta iteration 0 to be, theta bar transpose 0, 0, 0 for C's, and based on this, we assume this is the actually best estimate of theta. Then we compute the epsilon. Epsilon is basically comes from this expressions, right? This expression, and we can actually construct the epsilon. That's a prediction error. Basically, y minus y hat. Y hat is constructed to this, and with the current value of theta 0, we plug in here and plug in here. We can create the y hat, and then y hat is basically compared to yt. That's actually epsilon, right? And then the time t minus 1 to t minus nc, we construct this. All these are constructed with the assumed initial parameter theta, superscript 0. Okay, so with this, we can actually solve the at this first round, we can solve the least square estimate. So we do this actually m times. So construct this, and then least square estimate, which is actually unique solutions. We compute this, by using those phi t, with use of the previously determined best parameter values here. Okay, and the solutions, theta I hat is used for constructing next epsilon, and cycle through this m times. M is something you can pick, and then actually find the solutions. So unlike least square estimate, this is actually not a convex optimization problem. So worst case, it may face a local minima problem. You end up with the non-globally optimal value. But choice of this epsilon is clever. And then the choice of this ARX solution to be used as the initial value is a very clever idea. And actually, this gives a pretty good result in most cases. If the systems are very strong and nonlinear systems, this may not be the case, but I know this extended the least square estimate works pretty well in most cases. Okay, with that, actually, I just reflect a few things. So what we did today is parametric linear system identifications. I explained, why we care parametric representations. If you have some knowledge about the systems, exploit that knowledge and put together some parametric model that usually provides you with the very succinct representations. You can focus on the estimation of a few parameters. Okay, and then we introduced this is just for the linear system, the model structure, ARX and Rmax, finite impulse response, FIR, and then box Jenkins models. And they're all different depending on how the noise comes into the systems. And then we started with the ARX model, autoregressive with the exogenous input model. And then this one is good because it provides actually linear regression. So you get the, you just apply the, least square estimate, you get the optimal solutions immediately. Then we introduced the noise dynamics. So this is another very important point today. And the noise dynamics, we model the structure as basically some is consists of two parts. One is totally unpredictable, white noise, ET, and something having some kind of structure, and then that's a transfer function HQ. And then what we'd like to do is to identify both for the past dynamics GQ and noise dynamics HQ. And then actually in doing so, we apply, as far as we apply the prediction error method, we have to put together the best estimate, and then that is given by predictor y hat tt minus 1 is given by h inverse gq ut and then such and such. So this is functions of your observation of yt and the input you use in ut on time t minus 1 and further. So with that, we can predict this. And this one is based on the parameters involved in both GQ and HQ transfer functions. And then, unfortunately, however, such Armax, the system identification turns out that the parameters are not linearly involved in here, but instead, the best we can do is pseudo-linear regression. And then that actually requires some non-convex optimization, and we introduced the extended least square estimate today. So that is to solve this Armax problem. So basically Armax is actually most popular, and you see this in many applications. So one side is just for the pass, and then by the way, then just if you don't care the noise, and if you just estimate the for the pass dynamics, that's almost a straightforward problem, right? Almost a straightforward problem. But I know that is a case where the noise comes in as a bare ET, white noise. If instead there's some kind of colored disturbance, colored noise comes in, you end up with the incorrect estimation of parameter values. We call that biased estimate comes in. As we discussed a little bit further next week, you end up with the biased estimate, which is many people that don't notice, don't care. But in fact, that's actually a very important part. If you talk to some expert in the system identification, that's really key point. If you ignore such colored noise, you can't get the true parameter values. So that's actually something going beyond just a standard practice. Last Monday we discussed some of the naive method versus a little bit more educated engineers method, which is a correlation-based method, right? The difference is very clear, right? So educated engineers use a little bit clever, smarter way to shut out the noise that comes into the system for non-parametric model. But a parametric system idea is a little bit more involved, because one side, the clever thing is to use that structure to get the succinct model. You just reduce the number of parameters, which is great. But at the same time, depending on how the parameters involved in the system, depending on how the noise comes into the systems, you have some kind of a biased estimate. So eliminate that. We need to do something special. And today we look at the predictor. That's actually one step ahead. The predictor. That's actually the best way to get the right estimations. Okay. So far, any question? Okay. Does Armax method produce superior predictions compared to common filter innovations, because innovation should be white noise? Okay, that's very good question. Well, there's some kind of a gap between the part 1, part 2, and the part 2 in particular. We dealt with the state space representation, right? So, of course, you expect some system identifications for, state space. And also further, you expect that we should have some kind of model characterization where the process noise and the measurement noise comes into the systems. We need to characterize, we need to quantify the noise characteristics, even though we assume that those noise are basically white Gaussian. Yeah, there's some discrepancy between the two. Yeah, and 2 weeks from now, we look at the different method for system identification, which is called the subspace method. This subspace method is specifically for identifying the parameters involved in the state space, ABC matrices. That's actually big ABC matrix, not the actually polynomial, the ones we discussed today. That actually, method, subspace method is also very important method and increasingly popular. And then having good features that you can't get from model prediction and prediction error method. But still, it is very difficult to characterize and identify the noise dynamics separately between process noise and the measurement noise. And today we introduced the noise, just one channel, through which everything is really, is covered. But in common filtering, it is so important to distinguish between process noise versus measurement noise. And actually, in subsystem identification method, some advanced method in subsystem identifications allows us to some extent estimate the characteristics of the process noise separately from measurement noise. But that's actually a little bit advanced topic. We will not cover that, but to some extent, that's actually being done. So this is still the kind of open questions. How do you really actually get the models needed for common filtering? That's still open questions. Nonetheless, people use some combined method, such as some measurement noise can be identified as separate offline measurement separately. And actually process noise and focus on the process noise that can be identified through a system identification. Well, system identification is broad, and actually some oftentimes the systems is not that actually friendly for system engineers like us. You can't put the input, or you just want to check the measurement, the noise alone, but you can't get the right experimental data unless you run the systems. So you have to run the whole systems, then actually process noise versus measurement noise are very difficult to separate. So that's actually a difficult situation. So yeah, this area is still basically still open. Nonetheless, people being using this, with the very careful treat. So our max model, yeah, back to just the standard control system design that you run in 214 or 2140, largely based on the body plots as such. That's actually kind of the techniques that are very well connected to this, the topics I talked about today. In addition, the noise dynamics in many ways it's useful. Noise dynamics is useful if you can get to know what the sort of disturbance is coming, what the sort of noise is really coming through some channels with some clever algorithms, code, like this, just a few lines of codes. It actually, hold a different board game because you get the access to those signals which are really bothering us and perturbing this. But I know we can actually estimate better prepared for the that kind of noise coming into the systems. So okay. So any other questions?
I just had a question about the more, I guess, for the context oriented project 2. It in the data it says for problem 2 that it says extra credit. Is part 2 an extra credit problem, or is it a required problem?
Oh, I eliminated that extra credit. That particular word is still sitting there.
In the data it says that, but not on the PDF.
Oh, that's actually a miscommunication between me and then Nick. Yeah, we agreed that let's put the part 2 be not the extra credit stuff. This is just a main part. So part 2, you may have some difficulties to implement that, but but please communicate with Nick. He's the guy who put together that data, so he should be able to respond to your inquiry. Yeah. So before you waste your time, with some kind of a unclear part, please send an email to him, and then Piazza or whatever, to make that happen. It's actually part 2. Maybe the time consuming. I hope you will minimize the wasteful time and really learn something through that process. That's very important, right? Okay, with that, I finish it on time today. Yeah, so I'll see you more in the next week. Going to a little bit, the deeper part of the system ID, and then followed by subsystem ID for state space estimations. Okay, take care. Bye.